Hello everybody, so my name is Melvyn. I'm product manager at Clickhouse. So I've been working at Clickhouse for 4 years now, and today I will talk to you about some of the work we have been doing around Iceberg. But also interestingly enough, I will also talk to you about Clickhouse a lot, and I will explain you what's the core fundamental difference between how Clickhouse handle data versus how Iceberg handle data. So when we created Clickhouse a long time ago, like almost 10 years ago now, we had some assumption, right? The first thing was that Clickhouse needed to be used for real-time analytics. So we wanted to make sure that we had a system that was extremely fast and that could be used for use case where you wanted to have extremely low query latency. And we built a bunch of features around it, right? We added support for projections, materialized views. We built many different data types around it. So, for example, JSON. We added, a very granular data type to improve compression ratio and things like that. So there was a lot of thoughts about how can we make Clickhouse effective to query, and how can we make Clickhouse effective to insert data, so to lower as much as possible the latency when you interact with Clickhouse. And a big theme for us was to make sure that Clickhouse was self-contained, right? We don't want a user to install 10 different software in order to be able to use Clickhouse. You can just download one binary and get started very quickly. But as any database, one of the big challenges is to often get data into Clickhouse, right? So something that we spend a lot of time doing at Clickhouse is making sure that we're supporting all of the formats out there. And there is a lot, right? Clickhouse supports over 70 different formats. So you can read over 70 different formats, and you can write to over 60 different formats from Clickhouse. So we wanted to make sure that Clickhouse can be extremely interoperable, integrate with your data ecosystem, so with your queue, for example, like Kafka or Red Panda, or with your database, so you can query directly from your MySQL and PostgreSQL and do federated query maybe in Clickhouse. And lastly, what we want to do is to make sure that you also can work with your data lake with Clickhouse. So how do we do that? Well, first of all, to understand how do we do that, you need to understand how data is stored in Clickhouse. So here I'm going to dive into the engine and into the format, and it's going to be a journey, right? So first, when you insert data into Clickhouse, you have to understand that Clickhouse is optimized for batch insert, right? So you can take millions of rows, insert them into Clickhouse, and Clickhouse will process them without problem. What Clickhouse will not support well is if you are inserting one row per row. Like most of all app systems, Clickhouse will not like this type of behavior. There are workaround, right? We recently added a feature called asynchronous insert, where basically we create an in-memory buffer in Clickhouse, and you can send all of your insert into Clickhouse. Clickhouse will buffer all that, and then we'll be able to write them as a big batch. So that's how we try to insert data into Clickhouse. The first thing that we are doing when we are inserting data into Clickhouse is that we are storing your data in memory. And the second thing that we are going to do is we are going to sort your data before writing them to disk. And we are going to sort them based on a specific key that you are going to specify. And this key is going to be defined in an order by clause, but typically, this order by clause will be the same one than your primary key. So we take all of your data, we sort them by a specific key, and then we're going to write them on disk. And when we write them on disk, what we're going to do, because we want to be efficient, is we're going to write them in a columnar fashion, right? So all of your data for your first column will be written down on disk in a specific file. Same thing for the second column, same thing for the third column. But now the question is, how can we make sure that we can read this data efficiently? So what Clickhouse is going to do is, as we sort the data before writing them, we can actually create an index on top of your data. And to create this index, we are going to need to build some structure around it. So let's assume here that we have an index on the first column called C1, right? So we sort our data based on C1, and we're going to have them like this. And what we're going to do is we are going to try to create this index, but because we want to be memory efficient, Clickhouse is designed to store petabytes of data. If we had to create an index for every entry in your columns, that will be a lot for your index. So we're going to create what we call a sparse index. So instead of having one entry every row, we're going to create some what we call granule, right? And we are going to have only one entry per granule. Typically, the granule has a very large size. It's around 8,192, but it's customizable. You can change it if you want. If you want to have like a sparser index or a less sparse index, so you can choose based on your need. So once we have this index, once we have this structure to divide your data, what we're going to need to do is we're going to create this index file. So we're going to create a file that is basically going to track where your granule starts. So here, for example, for first mark, it's going to be called mark 0, and then we're going to have an entry for this specific mark. And we're going to do the same thing for each one of your granule. And now that we have an index, we can actually try to use it to read our data. So let's say I have this query here, right? This query is searching for my table for a specific city. What this query can do is it actually can go to the primary index, fetch the right granule, right? We can do a binary search through our index, which will be very efficient, find the right granule to read, and then we are blocked, right? We are missing some information because obviously we could try to go through the whole file, decompress the whole file, and try to go through it to search for the granule, but that's not ideal. Ideally, what you want to do is you only want to read only section of this file and decompress only some part of your file. So what Clickhouse is going to do in addition to that is it's actually going to create what we call blocks, right? And it's basically a way of dividing your data and grouping them. So, and on top of that, we are going to create what we call a mark file. And this mark file is going to basically keep track of the offset of your block and the offset of your granule. So when we actually run a query here, we can go directly to the index. Each file is going to have its own mark file. And we can go, okay, so we need to read the first mark. Let's go into the mark file, see what blocks and granule we need to read. We can very quickly find the offset of this block and granule and only decompress the right part of the file that we want to read and that we need to read. So Clickhouse can just process part of your file instead of having to decompress the whole thing. So that's how Clickhouse can actually leverage its index. We can also do the same mechanism for what we call skipping indices. So typically you have like your primary index, which is built based on your sorting key, but you can add skipping indices, right? So for example, min-max, right? So you want to be able to say, okay, for these columns, I want to be able to skip some granules. So we'll add a specific skip index in our files. And we can actually try to track the minimum and maximum inside a specific granule. And then we'll keep track of this value. And then when we actually query with a predicate on these columns, we can use our skip index and know which granule we need to read. So that's how Clickhouse will handle the storage. This approach has different problems, right? If you look at this, when you write, I don't know, let's say 1 million rows in Clickhouse, like once you do one insert in Clickhouse, you are going to write many different files, right? So for example, here for files for an insert with 3 columns, you are going to end up with 6 files, 7 files. Let's say you add 1 skipping indices, you end up with 9 files for 1 insert. So now the more inserts you do, the more file you are going to have. The more file you are going to have, the more complex it's going to be for your system to work. So especially in an era where we don't necessarily want to work on file system, but we want to work on object store, that can cause performance problem because the more file you have in your object store, the more likely you have to have higher latency to retrieve these files, and it can be a problem. So this type of parts called white part in Clickhouse have some limitation, right? The two are it's not very adapted for cloud storage because there is too many files. And the second one is that it's required too much memory to write this data, right? Because you have like one file per columns. It's going to consume a lot of memory for it. So we had to create a different type of parts. We created the compact parts in Clickhouse. And this is the second type of part that we have introduced in Clickhouse. And this one is interesting because instead of having one file per columns, we are actually going to compact all these columns together. We are going to compact all the marked files together, and we are going to end up with much less files. Like with 3 files, you can see that we were already able to divide the number of files by 1/3. So that's the second type of part that we introduced in Clickhouse. And this type of part is called compact parts. And it's also much more efficient for insert. It has a better memory utilization. That's some testing that I've been doing. So for example, I've inserted over 20 billion rows. And then I compare the performance when using wide parts and compact parts for different type of tables, and you can see that's first read. So for example, you can see for wide parts they are much more optimized for read, so they are slightly faster compared to compact parts, which are slower. And it's kind of makes sense because when you have more files, Clickhouse can actually be more efficient when reading these files and better process them in parallel. And this is another read, for example, where it's actually even more visible. So for the same table, but one with only wide parts and the other one with only compact parts, you have performance of 12 seconds on one and performance of 19 seconds on the other. So the question now that you know that we have two types of parts, like wide part and compact parts. One is optimized for read, the other one is optimized for insert. You may wonder, okay, but now it's very complex for me to actually manage that, right? When do I decide to use wide? When do I decide to use compact? The good news is Clickhouse will handle that for you, right? Clickhouse will do that as part of the merge process. As Arno was explaining earlier, we merge and do compaction on files, so to keep the number of files controllable, right? So Clickhouse will take multiple parts, merge them into larger parts, and over the merge cycle, Clickhouse will decide automatically if it needs to be a wide part or a compact part, depending on the number of rows you are going to have in your parts, right? So Clickhouse will automatically select the right parts to optimize the performance for the merge and for the read performance. So why do I talk to you about that? It's because in the context of Iceberg, it's actually because if you look at the structure of a Parquet file, it's actually very similar to the format of Clickhouse, and more particularly to the compact part in Clickhouse. If you look at the format of a Parquet file, basically a Parquet file will have it will be divided into what we call row groups, right, which will be a bunch of rows. And this row group will be divided into columns, right? And each one of these columns will be divided into pages. And each pages will have its own metadata to help you read and scan pages and eventually print some of these pages. And at the end of the file, you will actually have like a long footer that contain a bunch of metadata that can help you read more efficiently this Parquet file. And this is exactly the structure of a Parquet, of a compact format, right? So the compact format is extremely similar to a Parquet file. Hence why for us it was fairly easy to implement support for Parquet in Clickhouse, given that most of the functions that Clickhouse has on top of its own part format, we could apply them to the Parquet format as well. But there is still some problems, and now I'm going to talk to you about some of the bugs and issues we had when we worked and developed our Parquet reader and our Iceberg reader. So the thing is, over the last 10 months, we have been implementing a lot of features on top of Clickhouse and on top of Iceberg. We added support for Iceberg v2. We added support for more integration. And when you have a high velocity of development, well, then you start creating more and more bugs, right? So now we are in this situation where, like, we have like a relatively good feature completeness, but the feature becomes unstable. And I'm going to show you some of the bugs that we have, but before going there, like that's some of the format that we need to support Parquet is only one of them. Some iceberg tables are also based on Avro. When you read an iceberg table, you need to be able to read a JSON file, Avro files. So there's a lot of format that we need to support, and all these formats evolve over time as well. So it makes it very hard to maintain. And to give you an example, I can show you the story of our Parquet reader. Our Parquet reader started in 2019, so it was like almost 6 years ago. It was contributed by the community, and this is one of the nice thing about having an open source project is like a lot of features are actually pushed by the community, and we could just have to look at what the community wants and kind of drive the development from there. But the first support for Parquet was actually using Arrow library, which is an intermediary format to work between Clickhouse, Arrow format, and Parquet file. So it was great. We supported it, but we wanted to have a native implementation, right? So another community member started doing an implementation of the Parquet reader, but this time using native implementation without going through Arrow library. So the first pull request was merged, but it was primitive, right? It didn't support all the functionalities that Parquet supports, and we were waiting for more contribution. But the problem is that sometimes when you are working on an open source project, well, people have a life, right? And sometimes they won't start a project and they don't have time to finish, and this pull request becomes stale. So we were stuck with our initial Parquet reader and a second Parquet reader which was not finished. So at some point, it was already in, I think, 2014, when we saw that this pull request was stale for a while. We decided to put some engineering development into improving our Parquet reader. So we allocated our engineer for a couple of quarters to finish the implementation. And we actually called it yet another Parquet reader. So it's actually the Parquet reader v3, which we worked on it. We took a lot of inspiration from the incomplete pull requests and create the new Parquet reader v3, which we just released. And you can see that the performance of the native Parquet reader are much better than the old Parquet that was leveraging the Arrow format. So we actually had a performance improvement that can vary between 35 to 80% on top of queries. So you just have to upgrade basically your Parquet reader, which is just a setting to your query, and boom, you gain 35 to 80% performance improvement, which is quite nice. But all that comes with a cost, so that some of the bugs that we encountered during this development, deadlock, for example. So we had this nice Parquet reader, and we parallelized the read of the Parquet reader, but it appears that when you have some feature on top of an iceberg, sometimes you could be in a situation where you have a deadlock. So for example, when you want to apply equality deletes, you need to, so basically the Parquet reader, when we read a Parquet reader, we're going to spawn a bunch of readers that will help us process this Parquet file in parallel. And sometimes all this reader will be reading this file and will be in queue to keep reading this file, but some other thread might be able to spawn more Parquet reader to apply the iceberg transition, the iceberg deletion, and then you end up in deadlock. And the process stop waiting for more thread to be available to read more Parquet file when you can actually not do it. So that's some of the deadlocks that we had. And another bug that we had that was very interesting is that when you work on top of I will say open specification, sometimes some specifications are difficult to interpret, and everybody interprets it a bit differently. And that's the case around iceberg. So typically when you write an iceberg table, or if you want to write some specific data to an iceberg table, you are going to create metadata about your Parquet file. But the first thing you are going to do is first you are going to write your Parquet file, right? And inside your Parquet file, you are going to have different columns. And in these columns, you are going to have a column names. And normally these column names will be inside the Parquet file too. So for example, this is iceberg metadata. The iceberg metadata will contain the schema of your Parquet file. So it's telling you, okay, so you have this struct type, you have the schema ID, and then inside this schema, you have the following field. So here there is only one field, which is the field ID. It has an ID 1, it has a name, so this is my column C1, and this is not a required column, so it's optional. And then you have the type of your columns. So here you can see that the name of the column is C1, but some writer, for example, will not preserve the name of your columns within your Parquet file. So here, if you look at the Parquet file, you can see that we have a Parquet file that has a column name col1, which is slightly different than C1, which for Clickhouse, we were reading an iceberg table assuming that your column name in your iceberg metadata will be the same one than in your Parquet file, which is not the case, which is the case for most of the writer, but not all of them. And this one was actually right in the iceberg specification. You need to read your Parquet file using the field ID rather than the column name. So sometimes like specifications are difficult to interpret, and only some specific writer will apply some of this part of this specification, which sometimes make it a bit difficult. Great, so that's some of the problems that we encounter. Now what's next? So we're going to spend a lot of time improving the reliability of our new feature, right? So now that we have a bunch of new feature out there, people will test it, will report bugs, and we're going to spend some cycle fixing these bugs. But what we want to do now is we want to add support for the new Iceberg v3 reader. So specification of Iceberg evolve over time, and currently we are Iceberg v2 compatible, and we need to work on Iceberg v3 compatibility. We want to finish improving our Parquet reader, so there's still some optimizations that we are missing that we are still trying to implement, so there will be some change in our new Parquet reader. And as Arnaud highlighted it, we want to add write support to Iceberg and to Delta Lake. We also want Clickhouse to be able to do table maintenance on top of an Iceberg table. So that means that Clickhouse will be able to merge your Parquet file as well and remove some of this metadata that are in your Iceberg table. And finally, we have a bunch of projects for ClickPipe on our cloud offering. So we want to make sure that people will use their data lake as a source of truth, and they will use Clickhouse as a layer next to their source of truth, and we want to facilitate workloads that are imported from your Iceberg table into Clickhouse. So we want to add a CDC pipeline in ClickPipe so that we'll read the Iceberg table and load it into Clickhouse automatically, incrementally. And we want to make our cloud offering a bit more serverless. So currently when you deploy Clickhouse in our cloud, you are going to have a set of compute nodes that are going to run Clickhouse and that are going to be stateful. But given that Iceberg table and Parquet files and Delta tables are completely stateless, we want to make sure that Clickhouse can work what we call stateless worker. So you have to imagine a pool of nodes outside of your cluster that can execute query directly on top of your Parquet file or your Iceberg table or your Delta tables and just die after a specific query execution. So we want to make sure that customer can use our cloud to just do ad hoc query on top of their Iceberg and Delta table. And the last thing that we want to implement is a distributed cache in our cloud as well that can be used to read some of this Iceberg and Delta table as well. Great. Thank you very much, everybody. And if you have questions later, let me know.